Matetski, and he's also a recipient of the Frontiers of Science Award. And today he will talk about the KPZ fixed point. Please welcome.
Thank you very much for inviting me to speak here. It's of course an honor to receive an award for our work. So I'm going to talk about my joint work with Jeremy Quastel and Daniel Remenik, in which we characterized the KPZ fixed point. Right, so we want to model random growing interfaces. So here are 3 examples of growing interfaces in nature. So this is a sheet of burning paper, bacterial colony, and mountain range. So if you look, okay, let's look at the first example, the burning paper. So the fire front propagates down, and due to the inhomogeneity of the paper, it doesn't propagate uniformly, right? And the same can be said about the bacterial colony. So one of these spots started growing from, let's say, from one point, and then it was growing in all directions. So it got bigger, bigger, bigger. But again, due to the inhomogeneity of the environment, this growth is not uniform. So after some time, you see this rough boundary of the bacterial colony. Yeah, so it's very hard to describe such process precisely, and a natural tool would be to use some randomness, which describes this inhomogeneity of the environment. So what is a natural model which encapsulates key features of such random growing interfaces? I don't know, where should I stand on this side? Okay, so in 1986, Kardar-Parisi-Jung, 3 physicists, proposed the following stochastic PDE, the model to describe random growing interfaces. So this is the stochastic PDE, which is nowadays called the KPZ equation. And this is the equation which Ivan introduced in his talk. So here, H is one of these height functions. Let's say the height function for the burning paper. It depends on time and space variables, and it satisfies this nonlinear parabolic stochastic PDE. So the stochastic PDE has 3 terms on the right-hand side. The first term, the Laplacian, describes the smoothing mechanism of the interface. The random term given by the Gaussian space-time white noise describes low-range random perturbations of the interface. And the nonlinear term describes the slope-dependent growth of the interface. So the slope of the interface is determined by the derivative of the height function, and the simplest non-trivial nonlinearity depending on the slope is given by the derivative of h squared. Okay, so this equation is classically ill-posed, as Ivan explained, and it took mathematicians quite some time to make rigorous sense of this equation. It led to a huge progress in the field of stochastic PDEs. So in the paper, Kardar-Parisi-Jung also conjectured that under the suitable scaling limit, under the suitable rescaling, the solution to the KPZ equation should have a non-trivial scaling limit. So in other words, if we take a small parameter epsilon and we rescale the time variable, the space variable, and the size of the fluctuations of the height function by suitable powers of epsilon, this is called the 1-to-3 scaling. If we centralize the interface by subtracting some large deterministic constant, then when epsilon goes to 0, one expects to observe a non-trivial limit. So this limit is a random function on the space-time domain. So nowadays, this limit is called the KPZ fixed point. Okay, so maybe I should say that characterization. So proving this the scaling limit for the solution of the KPZ equation is still an open problem. So for very few particular initial conditions, it has been done, but yeah, by several authors. But to prove this limit for arbitrary reasonable initial condition is still open. So similar behavior was observed in other models describing random growing interfaces. So among them are such known models like ballistic deposition. So here is the picture. So in these models, blocks fall down randomly from the sky, and they get attached to each other. Okay, so we obtain after some time some growing interface. So another known model is the Eden model, which is a model simulating bacterial growth. So we have this spot of particles, and particles get attached to the boundary randomly with certain satisfying certain conditions. So there are many models which can be characterized, which can describe random growing interfaces, and only for few of them the 1 to 3 scaling limit has been proved. For several models, it has been proved for very special initial conditions. But for many models, okay, so for example, for such models like the Eden model, ballistic deposition model, like probably the most famous models, literally nothing is known. Just what we have is only the simulations which support this conjecture. Yeah, so let me tell you some interesting relation of the KPZ fixed point to random matrices. So if we start the KPZ fixed point with some particular initial conditions, initial states, then the marginal distributions of the KPZ fixed point will coincide with the Tracy-Widom distributions which appear in random matrix theory. So more precisely, if you look at one of these initial conditions, so the narrow wedge is when the interface starts growing from one point, or the flat initial condition, when at time 0 the interface was just constant 0. So then at time 1, the marginal distribution of the KPZ fixed point in these two cases will coincide with the two Tracy-Widom distributions, Tracy-Widom GUE and GUE. Okay, so the random growing interfaces have a connection to random matrix theory. Reference? Okay, well, there are many references to it. You mean the reference where, like, well, yeah, so there are many references. I decided not to provide any. But these are theorems. Right, as I said, for several models, the KPZ fixed point has been characterized for very few special initial conditions. And in our work, we managed to do it for arbitrary reasonable initial condition for random growing interface. So we characterized the KPZ fixed point as scaling limit of one particular model in the KPZ universality class, TSEP, the totally asymmetric simple exclusion process, which is probably one of the simplest models described in random growing interfaces. So let me introduce the model. So in this model, particles jump on the integer lattice with the condition that at any time, each side is either empty or occupied. So we don't allow several particles to sit at the same side. Okay, so this is a process in continuous time, and particles independently try to jump to the right. With only conditions is that they're not allowed to jump on top of another particle. So for example, if this first particle decides to jump, it is allowed to do it because the destination is empty. But then if this third particle wants to jump, then we forbid it because the destination side is already occupied. So the particles move to the right. So for each configuration of particles, we can associate the height function, which takes unit steps up and down. So the height function is built as follows. If there is a particle at a site, then the height function makes a unit step up. If the site is empty, then it makes a unit step down. So here we have two particles. The height function makes 2 steps up. Empty, down, particle up, and so on. So we have this height function h. And the evolution of this height function is described very easily. So if one of these particles jumps to the right, then the respective local maximum of the height function h turns to local minimum. Okay, so in other words, the height function moves down so that local maxima of the height function independently turn to local minima. Okay, so if you run the model for quite a long time, and if we zoom out the picture, then we will see something like this blue curve. Okay, so I should say that at time 0, the height function was this wedge, this gray curve, which corresponds to the so-called step initial condition. So the T-step particles were occupying all the sides to the left of the origin, and all the sides to the right were empty. Okay, so when time evolved, the height function moved from this wedge to this blue curve. Okay, so this blue curve propagates like a parabola, and it has some random fluctuations around this parabola. So to study the scaling limit, we need to wait for large time, and we need to look at the height function in this window proportional to the powers of t 1/3 and 2/3. Okay, so in other words, we take the height function of T-sep and we apply the 1 to 3 scaling, we recenter, and we want to compute the limit when epsilon goes to 0. So for this, we work with exact solutions of the model. So it happened that T-sep can be solved exactly. So what it means is the following. The first result was due to Schutz in 1997, who used the beta ansatz to show that the transition probability of n T-sep particles to go from one fixed state to another fixed state is given by an determinant of an n by n matrix. So that formula by Schutz is not suitable for asymptotic analysis because, of course, we want the number of particles to go to infinity, and then, okay, we need to do something with the determinant when the size of the determinant goes to infinity. So another useful result, another useful discovery was due to Borodin, Ferrari, Prahov, and Sasamoto in 2007. They rewrote the Schutz's formula in the form of a Fredholm determinant. So in other words, they looked at the multi-point distribution function of T-sep particles. So we fix some indices of the particles whose distribution we want to study, and we look at the probability that at time t, the nj's particle is located to the right of some fixed value aj. Okay. So they proved that this multi-point distribution function is equal to Fredholm determinant. Okay, so the Fredholm determinant is defined in a suitable space, and the kernel inside the Fredholm determinant has a quite nice structure. Okay, so it is surrounded by projections, which are defined here, but the kernel KT itself has the following formula. It has two terms. The first term is simply a power of some operator Q, which is just an indicator function. Okay, so we just take this indicator function, convolve several times with itself. And the second term is given by the sum of products of two families of functions, psi's and phi's. So the functions psi's are given to us explicitly by the contour integral, and you can see that these functions psi depend on the initial configuration of Tracy-Widom particles at time 0, this x naught. And the functions phi are given implicitly. So they proved that the functions phi are unique solutions of the following bisignalization problem. So these functions are polynomials of different degrees, which are biorthogonal to functions psi's. So in other words, if we take one of these psi's and one of these phi's with different indices, or the same indices, we take the sum over x, then we get either 0 or 1, depending on whether the indices of the functions are the same or different. Okay, so why this formula is nicer than the Schutz's formula? Because now on the right-hand side we have a Fredholm determinant. So the Fredholm determinants are natural generalizations of the usual determinants in the case when the size of the matrix goes to infinity. So this formula is more promising if you want to compute the scaling limit of the model. And the problem now boils down to solving this bisignalization problem to determine the functions phi. So another nice way to write these functions psi is in terms of the Charlie polynomials. So CK are Charlie polynomials here. These are the classic polynomials orthogonal with respect to the Poissonian weight. Okay, so then the formula for the function psi, which I showed you before, can be written as a shifted and weighted Charlie polynomial. So I take the Charlie polynomial, I shift its argument by x naught, which is the initial location of a suitable particle, and then I multiply by the respective Poissonian weight. Okay. So in other words, we need to find a family of polynomials which biorthogonalize such shifted and weighted Charlie polynomials. So you can immediately see that if you look at the step initial condition, when the first particle has location 0, second has location -1, the next one -3, -4, and so on, then here, so x naught n minus k will be just k minus n. And then k cancels out, and what we have is x plus n. Okay, so we just have the usual Charlie polynomial, okay, shifted by n, but n is a constant. Okay, so in particular, in this special initial condition, we immediately know what the functions phi are. The functions phi are just the same Charlie polynomials. Okay, so for step initial condition, we can easily compute the functions phi. For periodic initial conditions, so the computations are more involved. The functions phi are given by linear combination of Charlie polynomials, but still they can be written as a quite nice contour integral. So there are some other initial conditions for which these functions can be computed relatively easily. So for example, we can combine the step and periodic initial conditions. So to the left of the origin, we take the step initial condition. To the right of the origin, we take periodic initial condition. So the formula for the functions phi will be more complicated. I just didn't want to write it, but it can be done. It can be computed relatively easily. So in our work, we solved this bisignalization problem for any initial condition of Tracy-Widom. So we developed a method of solution which can be applied not only for the Bose-Ingles problems for Charlie polynomials, but also for some other families of polynomials. So the method itself is quite involved, and the formulas for phi's are also quite complicated, but it happened that the final formula for the kernel has quite beautiful form. Okay, so let me remind you how the kernel looked like. It was like this, containing two terms. Okay, so now what I need to do, I need to conjugate my kernel Q by powers of 2. Okay, so why do I need to do it? So before it was Q was just an indicator, this indicator. So if I conjugate it by powers of 2, then this kernel Q becomes a transition kernel for random walk. Okay, so this conjugation I can do for free because the Fredholm determinant is invariant under conjugations. So then the second term of the kernel, the sum of products of psi's and phi's, can be written as a composition of two functions, s and s-ap. So what are these functions? So this function s is given explicitly by a contour integral, okay, like this. The function s-ap, so here it is written, it is an expectation of another function s, and another function s is here. So, and what is this expectation? Inside this expectation, we look at the random walk B, whose transition kernel is this kernel Q. So this random walk starts at time 0 at the given location z0. It walks until it hits the curve x0, which is the initial configuration of particles. Okay, so in other words, we look at the stopping time tau, which is the first hitting time of the curve x0. And then the function s inside this expectation is evaluated at this hitting time and the location of the random walk at this hitting time. So you can see that the dependence of the kernel on the initial configuration of particles x0 is quite complicated. It is hidden inside this expectation, right? So it is, so dependence appears through this stopping time, hitting time of the curve x0. So for special initial conditions, which I showed you before, the distribution of this hitting time can be computed explicitly. So that's why we've got nice formulas in terms of contour integrals before. So if you take any initial configuration x0, then so computing the distribution of this hitting time tau is a complicated problem. Okay, you can compute it, but you don't get a beautiful formula. Okay, so having the formula in terms of this expectation, so it is more advantageous than trying to compute this formula more explicitly. Okay, so this is our formula for the kernel of T-sep. And if you want to study the scaling limit of T-sep, we need to study the respective scaling limit of the Fredholm determinant, which means that we need to study the respective scaling limit of this kernel. And what happens is that when we apply the 1 to 3 rescaling to the T-sep, in the limit, the parts of the kernel which you see in this formula, they get naturally replaced by the continuous analogs. So in particular, the transition kernel of the random walk converges to the transition kernel of a Brownian motion. So the random walk converges to the Brownian motion. The hitting probabilities for the random walk converge to hitting probabilities for the Brownian motion. So these functions s, which you saw in the formula, they also have nice limits. They converge to the kernels, these exponentials generated exponentials of the third and second derivatives. And these kernels can be written explicitly in terms of the area functions. Okay. So in other words, we can obtain the scaling limit of this kernel, which gives us the scaling limit of distributions, multi-point distributions of the height function of T-sep. And this allows us to characterize the KPZ fixed point in the sense of its multi-point distributions. Yeah, so the final formula, which is the main result of our work, looks like this. So H is the KPZ fixed point. We fix an initial state H naught, which is an upper semi-continuous function which grows at most linearly at infinity. And we look at the multi-point distribution. So the time is fixed, and the locations, spatial locations x1, xm are also fixed. We look at the probability that the KPZ fixed point at time t at given x stays below the given constant a. Okay? So this multi-point distribution function is given by the Fredholm determinant on a suitable space where we can write precisely what the kernel inside the Fredholm determinant is. So again, the kernel is surrounded by projections, which are here. And the kernel K inside is defined in terms of the so-called Brownian scattering transformation. So what is the Brownian scattering transformation? So remember, we fixed the initial state of the KPZ fixed point H naught at time 0. Now we look at the following probability. We look at the probability that the Brownian, so we look at the Brownian bridge on the time interval from minus L to L, so that the boundary values are U1 and U2. And we look at the probability that this Brownian bridge hits the hypograph of H naught on the time interval from minus L to L. So in other words, we have the Brownian bridge, which goes from one point to another point, and on its way, it goes below the fixed curve H naught. Okay? So we get a kernel which depends on two arguments, U1, U2. And then the Brownian scattering transform is defined in the following way. We take this hitting probability, we conjugate on two sides by the exponentials of minus L second derivative, and we take the limit when L goes to infinity. Okay, so then our kernel inside the Fredholm determinant has the following structure. Again, it has two parts. The first part is a transition kernel of the Brownian motion, and the second part is the Brownian scattering transform conjugated by respective exponentials of the second derivative. So one can show that, in fact, the kernel which we obtain inside the Fredholm determinant is a trace class operator. So in particular, the Fredholm determinant is well defined. So we proved the scaling limit of one particular model in the KPZ universality class, T-sep. And of course, a natural question is, can we prove the same limit for some other models? And for some models, we can do it, but only for those models for which we know exact formulas. So for example, the same scaling limits was proved for reflected Brownian motions, for several variants of T-sep, for example, T-sep in discrete time with geometric and Bernoulli jumps, polynuclear growth, which is another known model, classical model in the KPZ universality class. So the only attempt, as far as I know, to prove convergence of the KPZ fixed point of a model without using exact formulas was done by Quastel and Sarkar. So what they did is they looked at exclusion processes and they compared the distributions of quite general exclusion process to Tay-Sep. Okay, so that from convergence of Tay-Sep, they could conclude convergence of these quite general exclusion processes. They used some probabilistic tools, but it happened that this method worked only for very special initial conditions. Yeah, so still we have to rely on exact formulas. Okay, so in the rest of my talk, I want to tell you about one other interesting model, polynuclear growth, which we also managed to solve using our method. So the polynuclear growth PNG was introduced by Prohofer and Spon in the form in which I'm going to explain it, and its discrete version was known for already quite some time. Okay, so I found it in the paper by Gates and Westcott in 1995. So in this model, the height function is allowed to take, so it depends on the integer argument, and it is allowed to take either integer values or minus infinity. Okay, so a typical height function will look like this. It has integer steps up and down, and we just draw segments. We just draw the height function like by vertical and horizontal segments. So the vertical segments of the height function propagate with deterministically with unit speed. So this vertical segment propagates to the left, this one propagates to the right, and respectively for these vertical segments. So when the two segments meet, for example, this one, these two, when they meet, they just collide and disappear. So here, when they meet, they just collide and disappear. So at random location with intensity 2, unit steps appear. So these unit steps up and down, they appear randomly, and as soon as they appear, they start growing in two directions, as I just explained. Sorry, what time is it left? Oh, yes, so I have some time. So it is quite easy to model PNG. So if you look at the space-time domain, so here the horizontal axis is space, vertical axis is in time, and we sample a Poissonian point process with intensity 2. Okay, so these dots, these are the random dots. So at time, so this horizontal line corresponds to the time. So at time 0, we started here. Okay, and let's say the interface, the height function was flat. So when time evolves, this horizontal line moves up. So when this horizontal line crosses the blue dot, then the nucleation appears. So this unit step up and down appears on, at this location above the height function, right? So if you run PNG from time 0 up to here, then the height function will look like this. So it was known that the PNG model is exactly solvable, but again, the solution was computed only for very few special initial conditions. So we managed to solve it for arbitrary initial condition. So again, we look at the multi-point distribution function of PNG, and we can write to the Fredholm determinant. So the kernel inside the Fredholm determinant has the same structure as the kernels which you have seen before. But now all these continuous or discrete operators are replaced by some other continuous and discrete operators. Well, discrete in this case. Okay, so in particular, we need to introduce the symmetric derivative, discrete derivative, and the discrete Laplacian. Then the kernel has two terms. The first one is the exponential of the discrete Laplacian. So this d2 should be, in fact, the Laplacian. And the second term is, again, the scattering transform of a random walk conjugated by suitable exponentials. So what is the random walk in this model? The random walk is the one generated by the Laplacian. So it is a Poissonian random walk which makes unit steps up and down. Okay. So this hitting probability which you see inside the kernel is again given. So it is again the probability of the random walk to go from a given point to another given point, hitting the curve on its way, where the curve is the initial state of the PNG at time 0. Yeah, so in particular, from our formula, we can recover the previously known formulas for special initial conditions. And again, our formula leads quite naturally to the KPZ scaling limit. So we can prove that the PNG model converges to the KPZ fixed point. Okay, so I have some minutes to show you another interesting observation which we found. So we realize that the formulas which we obtain, I call these Fredholm determinants, surprisingly, are solutions to some known classic integrable systems. So for example, if I look at the one-point distribution function of PNG, okay? So this is our function f, which depends on 3 parameters: time, space, and r, which is the value in the distribution function. Then what we can show is that in a suitable region, this function is a solution to this PDE. So this PDE is a known classic integrable system, which is called the 2D Toda equation. Okay, so this is, at least to us, it was quite a mysterious discovery, because it is not clear at all what these different worlds have in common. So we were working with random growing interfaces, and we were obtaining formulas for random growing interfaces. But these Toda equations, they describe like models which don't seem to have anything to do with random growing interfaces. But somehow these two worlds of integrable systems, they somehow related. So in the case when we look at the flat initial condition, we start PNG at time 0 with a constant interface 0. Then from this equation, we can derive the classic Toda equation. So if you look at this, the distribution of the if you look at this function g, which is a logarithm of difference of 2 logarithms of the function f, then it just satisfies, is a solution to this quite simple equation, which is the classic Toda equation. Again, so it's just mysterious. How come these equations appear from those Fredholm determinants? So there is an analogous result for multi-point distribution function of PNG. So now I take n points, n spatial points, n values r, and I look at the multi-point distribution function, which I denote by f. Then what we can show is that the ratio of these two functions f is given by is equal to the determinant of some n by n matrix. And this n by n matrix Q satisfies, again, some quite nice equation. So it is a solution to this partial differential equation. So this equation is again something known. It's called non-abelian 2D Toda equation. So we know that the PNG converges to the KPZ fixed point. And we know that the formulas for PNG satisfy these classic equations, Toda equations. So the natural question is, are there some analogous equation for the distribution function of the KPZ fixed point? And the answer is yes. So quite naturally, by taking the scaling limit, we can obtain equations for the distribution function of the KPZ fixed point. Okay, so here again, so H is the KPZ fixed point, and I look at the multi-point distribution function of the KPZ fixed point. So time is the same. I fix different spatial points x. I fix different values r. So I take the logarithm, I take the derivative, and what I obtain is equal to a trace of a matrix. And this matrix Q is a solution to some PDE, which is again some known PDE, which is a matrix KP equation. So if I take the one-point distribution function, then this matrix KP equation simplifies, and we just obtain the scalar KP equation. And if we take again the flat initial condition, we start the KPZ fixed point at the value is 0 at time 0, then what happens is that the distribution function doesn't depend on the point x. And this term will vanish, and what we obtain is the KdV equation. So if we start the KPZ fixed point from flat initial condition, then the distribution function of the KPZ fixed point solves the classic KdV equation. Yeah, so we don't have any explanation to this at all. So we can perform computations to show that our formulas indeed solve these equations. But why is it like this? We don't know. And I think I will stop at this point.
Okay, questions?
Just on the slide before, you say you obtain the KdV equations. So do you have example of other models where you can get another dispersive equation, or just?
If I have examples of what?
You have no intuition why in the end you got the KdV equations.
No, we don't know. So we take our formula, Fredholm determinant, we perform computations, that's quite involved algebra, and we get the KdV equation.
And I have a more general questions. So here you presented different applications where you try to repeat the proof, but what is really the bottleneck? So you say that of course you need to have integrable systems for trying to work out this formula, but what is the most difficult part in this model? So in this works, like when you try to repeat the same arguments and.
Right. So we know how to works. Yeah. So basically, we know how to works for models for which we have Fredholm determinants, and the kernel is given by the solution to the Bayes organization problem.
Yeah.
This is So we know how to solve only these models.
Okay, so when you have this kind of formula, you know exactly how to solve this model. But if you are outside this framework, this is start to be.
No, then if you change the model a bit, then usually what happens is that these formulas don't work anymore.
Okay.
And then we don't know how to solve.
Okay. Thank you.
Okay, so here you have a multi-point distribution for your KPZ fixed point. Is it easy to deduce the property of the process if you've given the process in the spatial variable x, for example? Is it easy to get continuity of the process from this result?
Yes. Okay, so right. So I talked about only the multi-point distributions. So we also have a formula in which, okay, so sorry, where is it? yeah, so we also have a formula in which we look at the probability that h at time t stays below a fixed function. Yeah, so we also have formulas like this. But yeah, so continuity, I guess, right? So continuity, so we can prove continuities from these formulas. Right. So if we have Fredholm determinants, then we have quite good algebra.
Can you explain why the quadratic term is so important?
Quadratic term where?
In the KPZ equation.
Oh. So which direction am I going? Here. Well, so you have your height function h, and you want the growth of the height function to be slope dependent. So if the slope is bigger here, then the growth is bigger. If the slope is smaller here, it's like this, right? So it means that the nonlinearity should depend. Yeah, so the slope is determined by the derivative of the height function. So it means that the natural form of the equation which you would expect will be like this. So the slope dependent growth is given by some function which depends on the derivative. But then, okay, so what is the simplest interesting function? So linear function is just too simple, but yeah. So so if you just take f to be the linear function of the derivative of h, then this equation becomes too simple. It's non-interesting. It's linear. But then, so the next interesting example will be when you take the derivative square. It's just the simplest function f which you can take.
Do we have more questions?
Or there are such reasons.
Physical reasons. Okay, so there is a conjecture that basically whatever function f you take here sufficiently nice, then there should be some rescaling under which you will obtain the KPZ equation with the quadratic nonlinearity. But I'm afraid I cannot explain. I cannot give more intuition behind this.
Okay, maybe some question not related to this. If I didn't remember wrong, so the Fredholm determinant of LPP, the last passage percolation, can be factorized because the term on the right hand side should be 1 plus can be 1 plus some matrix can be factorized as a n times 1 matrix times a 1 times n matrix, right? So is that a special case of what your method here?
Okay, I don't n times 1 matrix.
Yes, because in determinant you can change the order of the something inside this, and then it can be estimated just as a one-dimensional case.
Okay, I don't really know if there is a formula for, as you're saying, by n times 1 times n. But so in the last passage percolation, Okay, so last passage percolation is coupled to T-sep in discrete time with, I guess, geometric jumps and parallel update, and it corresponds to the T-sep with step initial conditions. And so in this case, like the formula which you obtain simplifies. Okay, where is our formula? Yeah, here is our formula. So this heating problem becomes trivial. And what we obtain is just the second term is given by just S composition with this S, like the composition of these two S. But okay, it doesn't sound like the formula in the form which you are saying about.
Okay, thanks.
Do you have more questions? If not, let's thank the speaker again.